CERN blew the world up in 2008. It's been predicted repeatedly that CERN will wipe off the universe and all of its inhabitants. And it looks like this prediction is coming true more than ever thanks to the strange experiments conducted by the Large Hadron Collider. Leading scientists at CERN have identified a new particle that has the potential to change everything. In his Joe Rogan Experience podcast, Joe Rogan said that some of the unusual occurrences occurring globally might be related to these dangerous trials. Isn't it odd that these significant discoveries are being hidden by the mainstream media, even though this discovery has the potential to be greater than life itself? And maybe the biggest discovery made by humans to date? There's a reason they are hiding this significant discovery. What could they have discovered at CERN? If something were to go catastrophically wrong, what would be the consequences of that happening? Join us as we investigate the mystery surrounding the Large Hadron Collider as Joe Rogan makes a chilling announcement. A number of perplexing occurrences at the European Organization for Nuclear Research in the past few months have piqued the interest and concern of both scientists and the general public. The exact nature of these events is unknown, but they highlight how complicated and mysterious particle physics is, and how much more research is needed in this area. Although CERN primarily focuses on the universe's most basic particles and the principles of physics, it has also produced other significant scientific breakthroughs. For instance, the idea of a distributed information system was put forth by physicist Tim Berners-Lee in 1989. That system evolved into what we call the World Wide Web. In fact, the world's first web page was for CERN. Still expanding our understanding of the cosmos is the primary goal of most CERN research. Countless scientists do tests purely for the sake of understanding the workings of natural laws, completely disregarding any consideration of practicality. Scientists sometimes call this pure research. 20 member states from Europe currently run CERN. Both the duty of supporting CERN and the honor of directing activities at CERN facilities are shared by these nations. Additionally, CERN has international partnerships that let other nations use its laboratories for research and experimentation. Could CERN really bring an end to life as we know it? And how can a single institution utilize a contraption like the Large Hadron Collider to solve enigmatic global mysteries? In the history of particle physics, CERN has consistently been the vanguard of groundbreaking discoveries. But here we are dealing with something quite different. Particle acceleration tests have shown unexpected anomalies and unexplained data changes over the past year. A perplexing discovery revolves around the LHC's detectors, which have on occasion captured strange particle signatures and energy levels never seen before. These discrepancies seem to contradict the established rules of particle physics, which makes them all the more puzzling. Scientists have been painstakingly going over and re-examining their data, but they still haven't found what's causing these outliers. In addition, some anomalies in the LHC's surrounding magnetic field have prompted conjecture regarding possible environmental causes. CERN's underground facilities have always functioned in close proximity to one another, thanks to their deliberate design to minimize outside interference. Curious about the origin of these disturbances, however, include seismic events, variations in Earth's magnetic field, and unexplained fluctuations in the LHC's magnetic shielding. Some scientists have been looking into the CERN experiment, and one theory is that this particle could be a larger, heavier version of the Higgs boson, or the God particle. If this is true, it could lead to a complete rethinking of our knowledge of the universe and its workings, as well as the opening of gates to other planets. But would this be a good thing? If this story is true to its core, this particle would be 4 times heavier than the heaviest known particles the biggest quarks, and up to 6 times larger than the Higgs boson. A God particle, a theoretical possibility initially proposed in the 1960s. Second, and most intriguingly, the spikes could be evidence of a newly discovered theoretical particle called gravity. Gravity helps mediate all gravitational force. Some prominent scientists think this particle could open the door to other dimensions in the universe, but with what consequences? Others have even gone so far as to say that it's all an elaborate hoax and that they've actually found new worlds. They're just slowly letting us in on the secret. The most recent finding followed the discovery by scientists at CERN of unexpected spikes in photon particles in the data from 2 LHC detectors. Reportedly, spikes reached 750 giga-electron volt peaks, which are thought to have been produced by massive high-energy proton collisions. French scientist Adam Falkowski started the conjecture after tweeting about the significance of the spikes. This enormous discovery could cause alterations to the standard model of the universe's interactions. Quite literally, this has the potential to alter our whole understanding of the cosmos and everything in it. Adam Falkowski posits that this particle is likely to be a minor component of a more substantial whole, maybe related to electroweak symmetry breaking and the standard model's hierarchy problem. A new golden age in particle physics might be on the horizon if the signal turns out to be genuine. A paradigm shift would occur if the findings really do depict a novel particle. In terms of originality, the Higgs boson is completely outdone. How exactly does the Large Hadron Collider function, and what is its actual purpose? The Large Hadron Collider can recreate the same conditions from the early universe. While some regard it as the key to understanding the cosmos, others worry it could wipe out Earth's biosphere. The LHC forms the heart of a vast accelerator complex near Geneva. It unleashes tremendous energy that collides catastrophically by shooting protons and ions into beams that are almost as fast as light. The LHC painstakingly records the particle showers produced by these massive collisions, with the expectation that a better understanding of the universe's structure and how everything came to be can be gleaned from these brief periods. Although the LHC may not be immediately useful, its promise of greater understanding is what makes it worthwhile for both the thousands of scientists from around the world who work together and compete. The Higgs boson particle was one of many secrets of the universe that the Large Hadron Collider has helped to unveil. A theory known as the Standard Model was put forth by scientists in an attempt to comprehend the structure, operation, and workings of our universe. The basic building blocks of the cosmos are an effort to be defined and explained by this hypothesis. It tackles 3 of the 4 fundamental forces in the universe: the electromagnetic force, the weak nuclear force, and the strong nuclear force. By combining ideas from quantum theory with Einstein's theory of relativity, gravity is the 4th fundamental force. Although it doesn't deal with its effects, numerous predictions regarding the cosmos have been put forth by the Standard Model. In 2012, the existence of the Higgs boson particle was verified thanks to the LHC, which was one of its key predictions. If we want to know why certain subatomic particles are heavy, we need to look no further than the Higgs boson. The Higgs mechanism postulates a particle and a matching force that gives other particles mass, even if neutrinos and some other particles don't have it. The revelation has prompted scientists to keep exploring the LHC for more information and new ideas. The primordial era of the cosmos is the subject of yet another matter-related mystery to scientists. The cosmos began with matter and energy interacting, particles of matter and antimatter destroying each other immediately following the separation of energy and matter. Both matter and antimatter would have balanced each other out if their quantities had been identical. The universe did include some antimatter, but luckily there was also some matter. Scientists hope that they'll be able to observe antimatter during LHC events, which might help us understand why there was a minuscule difference in the amount of matter versus antimatter when the universe began. Research on dark matter is another area that the LHC is focusing on. Based on what we know presently, observable matter accounts for around 4% of the total mass of the universe. A large quantity of invisible substance known as dark matter, which makes up approximately 25% of the universe, is revealed by the motion of galaxies. Dark energy, the alleged driver of the expansion of the cosmos, is assumed to account for the rest. More tests at the LHC, according to scientists, should reveal more about these mysterious parts of the cosmos. By smashing protons together hard and fast enough, the LHC causes protons to break apart into smaller atomic subparticles. These tiny subparticles are very unstable and only exist for a fraction of a second before decaying or recombining with other subparticles. However, these minuscule subparticles made up all matter in the early cosmos, as postulated by the Big Bang theory. Larger particles such as protons and neutrons were formed when these smaller ones combined during the expansion and cooling of the universe. Some scientists think the LHC could find proof of extra dimensions. If the unusualness of theoretical particles, antimatter, and dark energy isn't enough, we're used to living in a world of four dimensions, three spatial dimensions, and time. However, there are physicists who have postulated the possibility of other unseen dimensions. A multidimensional cosmos is necessary for the plausibility of certain hypotheses. One formulation, string theory, stipulates the presence of 11 dimensions. Those who believe in string theory are hoping that the results from the LHC will lend credence to their cosmic model. String theory states that the fundamental building block of the universe isn't a particle, but a string. There are two types of strings, open-ended and closed. They have the ability to vibrate as well, much like the strings of a guitar do when played. The strings seem to be different things when vibrated in different ways. An electron would seem like a three-dimensional vibrating in one direction. A neutrino would be an alternative string vibrating in an opposite direction. There is no evidence to back string theory, according to some experts who have rejected the hypothesis. One thing that physicists can't accomplish without a supplementary theory is to include gravity in the standard model. String theory does just that. It brings the quantum field theory into harmony with general relativity, Einstein's thesis. However, the existence of these strings remains unproven at this time. There is no technique to detect them because they are too little to be seen. Because of this, some researchers have written off string theory as a philosophical concept rather than a scientific one. String theorists are holding out hope that the LHC will sway skeptics. Supersymmetry is something they're trying to detect. The standard model states that for every particle, there exists an antiparticle. A positron is the antiparticle of an electron, which is a negatively charged particle. Particles, according to supersymmetry, also have superpartners, who also have corresponding antiparticles. The LHC may confirm the existence of these superpartners, even though we haven't found any evidence of them in nature. If superparticles exist, they may provide light on the nature of dark matter and make it easier to include gravity in the current standard model. The basic idea of the LHC is not complicated at all. To begin, you'll need to direct two pathways, one clockwise and one counterclockwise, to launch particle beams. Both beams are accelerated to nearly the speed of light. You can then observe the results by pointing the two beams in the direction of each other. The tools needed to accomplish that objective are far more intricate. The Large Hadron Collider is merely a component of the Comprehensive Particle Accelerator Complex housed within CERN. A number of processes must be completed before protons or ions can enter the LHC. Scientists face a massive challenge with the 15 petabytes of data collected annually by the LHC detectors. With such data, how does one make sense of it all? Within such a massive data set, how can one tell if they're examining something meaningful? That much data could take thousands of hours to process, even on a supercomputer. Meanwhile, the LHC continues accumulating even more data. CERN's solution to this problem is the LHC computing grid. The grid is a network of computers, each of which can analyze a chunk of data on its own. Once a computer completes its analysis, it can send the findings to a centralized computer and accept a new chunk of data. The method is effective so long as researchers can partition the data. Grid computing is the term used to describe this method in the computer industry. The researchers at CERN have settled on utilizing low-cost hardware to execute their calculations. Commercially available, network-ready gear is CERN's primary focus, rather than state-of-the-art data servers and computers. The LHC enables scientists to see particle collisions at an unprecedentedly high energy level, surpassing any prior experiment. Some are concerned that the planet could be in for some major disaster as a result of such massive reactions. Some were even worried enough to sue CERN in an effort to put off the LHC's activation until later. In what ways will CERN shape the cosmos in the years to come? Identifying the project's pros and cons will help us delve into CERN's mission and the reasons some are worried about the organization's action. According to our understanding of the universe, the matter we can observe only accounts for about 4% of all the matter that exists. Physicists have proposed a kind of substance called dark matter that might make up to 25% of the matter in the universe. When combined with what we can see, the other 75% might come from dark energy. Some scientists at CERN hope the LHC will uncover evidence of dark matter. Additionally, black holes could be created by the LHC. Singularities are points of infinite density that matter is compressed into by a black hole. Compressing matter to such a degree is generally considered negative. Some are concerned that the black holes created by CERN could wipe out the planet. According to researchers at CERN, any black holes produced by the LHC will be quite tiny, harmless, and decay nearly instantly. CERN might discover a hypothetical particle. One of the big mysteries of the universe deals with mass. Why is there mass? What determines if a particle has mass? A theory called the Higgs mechanism says that there may be an undiscovered particle that could explain mass. Controlled collisions within the LHC could produce evidence of this particle. Strangelets, a potentially harmful material, might be released onto Earth by CERN. Strangelets are completely hypothetical, just like the Higgs boson. However, strangelets are extremely unpleasant clients, in contrast to Higgs particles. Some claim that this substance has the ability to break down and reassemble any substance it comes into touch with, resulting in an unusual substance. Strangelets have never been seen in nature, according to CERN experts, and even if they were, they dissipate before causing any problems. Even if they did, time travel is only one of many incredible real-world possibilities that could emerge from our expanding knowledge of the cosmos. According to some physicists, the LHC has the potential to become the first time machine in the world. They claim that going back in time could only be feasible up until the first time machine was invented. However, these theories failed to persuade other scientists. If our knowledge of the cosmos continues to expand, a future supervillain may have access to data that could endanger all of humanity. To be fair, the fact that CERN is not located near Metropolis makes this scenario highly improbable. The fact that the LHC will generate the most energetic particle collisions ever witnessed on Earth, together with worries about radiation, are additional reasons for concern. The LHC is 328 feet below and has extensive shielding according to CERN. Thus, it is completely safe to use. On top of that, no one is to be present underground while experiments are underway. Concerning the possibility of collisions, experts note that high-energy cosmic ray collisions occur naturally. Frequently, interactions between rays and the Sun, Moon, and other planets occur. However, none of these celestial bodies appear to be in danger at this time. The Large Hadron Collider will allow for the controlled collision of such particles. Beyond that, there is really no distinction. Ultimately, it appears like CERN has everything under control. The world is still standing after their experiments, which mimic real-life conditions. The one and only distinction is the stringent control and observation of laboratory conditions. Either way, CERN's activities could have a profound effect on us here on Earth. But the rest of the universe is likely to stay the course, expanding continuously with little regard for what we get up to down here on our planet. Will the LHC be able to add to our understanding of the cosmos? Are we likely to get more questions than answers from the data we collect? We may fairly safely infer that the answers to both of these questions are yes, if previous trials are any clue. Thanks for watching another episode of Space Voyager.